Hello, biologists. Welcome to class. Today we're going to talk about climate change effects. We're going to focus specifically on our area, on the state of Oregon. We're going to talk about how we measure the effects and what kind of effects we're seeing. This lecture is going to be a diagram and a graph bonanza, so make sure that you can visually see the PowerPoint as I'm talking because we're going to see a lot of diagrams. The first is 10 trackable indicators of climate change. What does trackable mean? It means quantifiable and easy to measure repeatedly. So these are data that we are taking continually to see how climate change is progressing. Let's go through them. First, as we warm our planet, we're going to heat our oceans. As we heat our oceans, we're going to decrease sea ice. That's going to increase the sea level. We're also going to increase the surface temperature of the sea. We're going to increase the temperature over the oceans. As we have this evaporation happening, we're going to increase water vapor. That's also going to increase the air temperature up in the troposphere. All of that warming up, even warming up over the land, is going to decrease the glaciers and the ice sheets. We're also going to decrease snow cover. So that's our first 10 indicator of climate change that we can accurately measure every year. Here we have temperatures in the contiguous 48 United States. What does that mean? That means just in the main landmass. So we're not including Hawaii or Alaska or any of the other territories of the United States. When is this through? 1901 to 2021. What do we have on our graph? We have the year. That's going to be our independent variable. Please identify independent and dependent variable every time we look at these graphs. Independent is usually on the x-axis, but it's the thing that changes. And then dependent variable, that's our temperature anomaly. That's going to be on the y-axis. What does anomaly mean? This is the temperature deviation from the average in a period of time. So it's going to tell you the period of time if you look at the original article. And I have all of these things linked for you in the PowerPoint so you can go and explore the data by yourself. There's a lot going on in this graph. Let's check it out. Here, 0 would be if there's no range from average. If it goes up, we have an increase in temperature. So this is a hotter than average year. If it goes down, we have a decrease in temperature. This is a cooler than average year. Our temperatures are denoted from the Earth's surface, if it's a bar, and from the troposphere, measured by satellite, if it's a line. So we have two different ways to measure temperature. What's the point? What's the overall trend? We have up and downs when we get into the industrial area up until the 1950s, more up and downs until like the 1980s, and then from 1980, let's say 6 on, we have a notable pattern of increasing temperature in the United States. So it's a distinct, notable increase. All of these bars are notably higher than they have been in the past. So that's one of the effects of climate change, is just increasing temperature. Let's look at some more data for that. Here is the annual average air temperature since 1901, again for the contiguous United States, but also including Alaska since 1925. Here is our rate of temperature change. We have Fahrenheit per century. And if it's blue, it is a negative change, meaning that it was colder. And if it's red, it's a warmer change. So it's increasing temperature. What's the trend we see? We definitely have high increasing temperatures in majority of the United States. Alaska is seeing climate change happen way more intensely and way more quickly than other places on the Earth. And we also have pockets that are seeing no change or are getting colder. So that's one of the reasons that we moved away from saying global warming, because there's not equally one outcome for climate change. We're going to have variable outcomes depending where you are. Latitude and longitude and habitat have a huge part to play in that. So really interesting that there's going to be some places that have cold and some places that have hot, but we do see a distinct trend. The majority of the United States has been warming the last 100 years. These are the temperatures worldwide. It's the same date range, so 1901 through 2021. We have the same independent and dependent variables, and we have the same way that we are measuring the data. So we have Earth surface temperature, that's just taken with a thermometer in different locations around the world. And then we have lower troposphere measured by satellite. That is the temperature measured up in the atmosphere. What's the trend? A definite shift from colder than average to hotter than average. Remember, anomaly is variant from the average. So a definite trend toward warming. I have a video for you. It is from NASA and it is going to go through global climate change measured as a heat map over time. The way a heat map works is cooler areas indicate a negative change, just like we saw in that graph where the temperature anomaly is cooler, and warmer colors like yellow and orange, and we're going to see a lot more red toward the end of the video. Those indicate a correlation with a higher than average, a hot anomaly for temperature change. Temperature is really easy to quantify and easy to measure. That's why it was one of those major 10 indicators in so many different places on our first diagram. We had toposphere, we had surface area, surface sea level, we had above the sea, we had land. Temperature is pretty good data, but it does get more complicated than that. So it's more nuanced. And let's talk about some of the nuanced effects of climate change. One is going to be changing weather patterns. So we are going to see an increase in extreme weather events, and we are going to see that be variable. So it'll be harder to predict. In general, weather is harder to predict. And so we're going to see more rainstorms, more lightning storms, more flooding. We're going to see more tornadoes in the Midwest. We're going to see more hurricanes. And that is an expected outcome of all of the changes associated with greenhouse gases warming the atmosphere and causing those 10 variables like decreasing glaciers and snowpack, increasing sea levels. We also are going to see ocean acidification. I'm adding this to the more complicated indicators because it takes about 200 years for 80% of the carbon dioxide that we release today to be absorbed. So whatever we're doing right now, we're not even going to see the overall effect for 200 years from now. And that doesn't mean we shouldn't try to make changes now. It just means that our predictions are based on an unknown outcome. We know that we're going to have a loss of biodiversity, and a major part of that is going to be habitat loss. These are totally a Venn diagram with loss of biodiversity. We're going to have economic impacts of natural disasters, those extreme weather events, sea level rise. We're going to have the cost of mitigating these changes, like trying to prevent sea level rise from washing away neighborhoods. That's going to cost a lot of money. It's also going to cost a lot of money to try and move people out of areas that are too damaged to stay. So that's called migration. Mitigation and migration are going to be a huge economic impact. We're also going to have health impacts. So we're increasing disease, and I have a slide on that coming up too. We're increasing the loss of crops, and so that's going to see an increase in starvation and malnutrition. We're also going to lose access to clean, fresh water. That's going to lead to dehydration and diarrheal diseases. And I added grief because the health impacts are not just physical. We have to think about mental health of all of the stress and the loss that is going to be associated with climate change. All right, now let's start to get into Oregon specific. So Oregon climate impacts and costs. We're going to start with higher temperatures, hotter temperatures, and then we're going to move on to our different types of effects of climate change. Here we have a graph. Global average temperatures per year compared with the pre-industrial age, 1850 to 1900. We have our pre-industrial age as before 1940. Then we have up to 2025. I think there's 5 bars after 2020. In 2024, the global average temperature was almost 3 degrees Fahrenheit warmer than it was in the pre-industrial period. In Oregon, in our state alone, the average temperature has increased 2.2 Fahrenheit per century since 1895. What about how hot will it get? Well, we have predictions. So here we have observed and projected changes in Oregon specifically, average annual temperature relative to 1950 through 2014. So that is our reference line that we are calling zero. Remember, when we're looking at differences from baseline, we need a baseline. So our baseline is based on 1950 through 2014. This graph is showing us three projections from today. So here's the bar where today stops and the projections begin. And these projections are based on shared socioeconomic pathways called SSPs. SSPs are predictions when we think about what different nations will do, how greenhouse gases will go, and what kind of climate actions might be taken. So they are more than just numbers of data. They are projecting what countries and people are going to do. The colored bars, which are these colored bars over here, are observed values from the National Centers for Environmental Information. And the solid lines, here are your solid lines. They're a little bit harder to see in these bars, but this is one, and this yellow is a line. The solid lines are the mean values of these simulations from 7 to 11 downscaled climate models. So they're using predictions. So this is a whole lot of computer programming to try and guess what's going to happen. What should we be paying attention to? We have our independent variable on the x-axis. We have our dependent variable on our y-axis. And we have actual data in the bars that are red and blue. These are years where the average temperature was higher than our baseline, and these are years where it was lower than our baseline. We can see we have a lot more red recently than we did historically. And now we get into the predictions. So from this point forward, three lines come out. We have this kind of maroon line that is a high level of climate disorder. And if that occurs, they project that we will be within, what's that, 9.5 degrees Fahrenheit by the year 2100. So that would be a 9-degree increase. That's pretty notable. It's going to have a really large effect on the habitat. Then we have this orange line. This is our mild projection, and our mild projection takes us out to just over 8 degrees Fahrenheit. And then we have our more conservative projection, which takes us out to just about 6. These bars here, so this yellow bar is showing us the deviation that might be in this range. So it could be as low as under 4. And then here, this orange bar from, let's just say 9 to 6.5. And then the concern is this bar here that spreads so high. There was some variation. It could be up to almost 14. In the next 50 years, the mean annual temperature is expected to be about 5 degrees warmer, and in the summer, up to 7 degrees warmer. That's a lot. Heat waves, especially week-long heat waves, are expected to be 2 to 7 times more likely between 2021 and 2050 as compared to our historic data. I have a screenshot here from June 2021 when we had that massive heat wave. Maybe you all remember it. It was pretty incredible, and we estimated that it cost Oregonians $1.3 billion, and we confirmed that it killed 96 people. So these heat waves, these effects of climate change are pretty disastrous. 96 people is a lot of people to lose to extreme heat. Thinking about hot days, the frequency of extremely hot days is increasing, and Oregon is expected to have 38 extremely hot days in 2050. An extremely hot day is a quantifiable measurement, so it's based on your location and your historical max temperature, so it's not the same everywhere. For example, 98 Fahrenheit is really hot, extremely hot in Medford, but in Portland, the city, 91 is considered extremely hot. Public services are disrupted when we have heat events. For example, only 15 out of 81 schools in Oregon's largest school districts have air conditioning. Maybe you went to a school that did not have air conditioning. We estimate that it would cost approximately $173 million to install AC throughout Oregon public schools. And if we're going to continue to have these heat waves, these week-long heat waves, and these extremely hot days, we're going to have to make that choice. Here we have a graph. This is a little bit wild, but let's break it down. We have number of days over 90. So in Oregon, that would be considered extremely hot. Sorry, in Portland, that would be considered extremely hot, but not extremely hot in Medford. And then we have the year, and we have Portland, Pendleton, and Medford. So three different cities in Oregon that we're comparing the changes of days over 90 degrees. Here is Portland. We have an upward trend, lots of variation. Then we have Pendleton, generally hotter than Oregon. Upward trend is pretty much in line with Portland, though. And then we have Medford. Note that Medford is the hottest, but also it has the steepest line of increase on this graph. So it is getting more hot days more quickly than other cities in Oregon. Not only do these extremely hot days require more planning and disrupt services, they also require a lot more energy. So this graph is from Portland General Electric. It's historic and projected seasonal peak load, and that is requirements of energy. Portland General Electric reports that extreme weather has become more common, and it is, quote, driving unprecedented hourly peaks that can require every available energy resource to meet demand, end quote. Let's look at this graph. Peak load in milliwatts, that's the amount of energy being used. They started collecting data in like 2006, and here's the data. We have summer and winter bars. Summer is red, winter is blue. Pretty consistent until about 2020. Then we have some really incredible spikes. Here we are in 2026. Summer is already requiring more than it ever has. Winter is at its highest level so far, and our projected usage is just continually upward. So that means that Portland General Electric is going to have to adapt as the climate changes, and we are going to have to adapt as we have to need more energy and have to pay for it. That brings us to a term called energy burden. Energy burden is the percentage of a household's gross income spent on energy bills. If it's 6%, it's considered high. And if it's over 10% of your gross income, it's considered severe. So if you pay more than 10%, you're severely burdened by energy. High energy burdens are correlated with a greater risk of respiratory disease, increased stress, economic hardship, and difficulty moving out of poverty. Here we have percentage of Oregon households experiencing high to severe energy burden and earning 20% or below federal poverty line by county. So we are thinking about our inequity in how climate change is affecting Oregonians. The yellow is 18 through 29%. The orange is 30 through 39%. And the pink is 40 through 49%. So that means like almost half of people are energy burdened, which is pretty amazing. Check out this, see if you have any patterns that you can identify. It's definitely affecting Eastern Oregon, Southeastern Oregon more than the rest of the state. And that is going to be our more rural area. And it's also going to be our more desert climate. So these are hot and dry areas that are going to feel the effect most. Hotter temperatures also lead to an increase in mosquitoes and an increase in ticks. And both mosquitoes and ticks are vectors for disease. For example, I'm using this as an example, but mosquito-borne diseases are increasing too. But for example, Lyme disease infections are increasing in Oregon. Lyme disease is spread by ticks. If you get bit by a tick that has Lyme disease, you'll often see this bullseye rash. And it doesn't always occur where you got bit, so it's not like you got bit right in the center, but it does occur most commonly. You can get Lyme disease without bullseye rash, but it's one of the indicators that we look for. Oregon had an average of 18 cases of Lyme disease per year from 2003 to 2012. And In 2013 through 2022, we had 48 cases, so way more than double. Oregon's coastal oceans have warmed about half a degree in Fahrenheit per decade since the 1950s. And Oregon is not feeling the change in our water temperature as severely as other states. So we are a little more slowly progressing in this. We're definitely feeling the temperature effects right now, but this is a more slow process. But just because it's a slow process doesn't mean that it's not having an impact. In 2015, an ocean heat wave led to the loss of 150 million from the Dungeness crab industry. And as our ocean temperatures change, we're going to disrupt upwelling cycles. And as we disrupt upwelling, we're going to see lower oxygen levels, we're going to see higher ocean acidification, and we're going to see more harmful algae blooms. Hotter temperatures have also caused more evaporation in the soils, and that leaves the soils drier. The hotter temperatures also decrease snowpack. Both of those things lead to more severe and more frequent droughts. This is also important for Oregon because we have a $5.7 billion agricultural industry, and 85% of our water in our state is used for irrigation. Here I have a list of the national ranking of Oregon agricultural products in 2023. This is how much of that product our state produces for the United States. So 99% of hazelnuts and crimson clover come from Oregon. Now, this is important because not just do we make money, this is also livelihoods, this is cultural, there's a lot going on. And we can measure where we think plants are going to grow using something called plant hardiness zones. So this is the United States Department of Agricultural Plant Hardiness Zone map, and it classifies zoning areas where different types of plants will grow. So if you ever flip through a seed catalog, it'll say for zone 5B or zone 8A, and that will tell you what regions would be good to plant those seeds in. If you plant the seeds outside of their zone, it might be too hot or too cold for those seeds, and they probably won't grow very well. There's 13 zones. Zone 1 is the coldest. Zone 13 is the hottest, and it has a 10-degree Fahrenheit range. These changes go from -7 in green to gray, which is -1 to 1. And then our warmer colors go from 1 to +7, which is in red. What does that mean? That means that the areas that you could plant these plants have changed this much in temperature, and that's going to shift where we're able to grow agricultural products. As the 99% producer of hazelnuts, if our hardiness zone changes enough that we are no longer able to grow hazelnuts, that's going to really affect the agricultural businesses in Oregon and our overall GDP in Oregon. So this is why we're talking about hardiness zones, not just because we love to garden. What do we see as a trend? Lots of cold changes over here in green, lots of hot changes over here in pink, and lots of hot changes over here in pink. Majority is having a change though. This like mustard colored, all of this is 5 to 7 degrees change. That is pretty incredible. So we are going to see a shift in how we are planting agricultural products. Let's look at Oregon's change. So this is the same range, 2023 to 2012, and we are looking at the change in temperature of plant hardiness zones. So we have colder areas here. We have gray with no change, so they do not have to worry about updating their agricultural products. And then up in the northeastern area, we have a lot of strong hot change. So remember this mustard color, this is the above 2 degrees Fahrenheit temperature change. So there's a lot of change here, a lot of change on the coast. This is going to affect us. We need to be thinking about what's going to happen in the future. All of these hotter temperatures are going to lead to more frequent and severe wildfires. The mean size of all wildfires have increased from 79 acres in the 1970s to a mean, an average of 6,769 acres between 2020 and 23. That is a phenomenal increase. So just think about how much more space is burning. In our area in the Pacific Northwest in 2020, we had wildfires that killed at least 9 people, destroyed 5,000 homes, and burned over 5 million acres. Check out this 2020 wildfire map. There's just no safe place. And this is going to continue to be a trend. We're going to see more and more frequent and more severe fires. We're also going to see, after those fires, more landslides. So if we burn all the vegetation, that means that the erosion control and the soil adherence is going to decrease. And we're going to see more debris flows and flash floods. It is estimated by the year 2100, the frequency of extreme rainfall occurring within 1 year of a wildfire will increase 700% in the Pacific Northwest. So we're going to have a lot more of these earth movement changes that will disrupt our lives. We're also going to have an increase in rainfall because hot air can hold more moisture, and more moisture is going to lead to a more intense water cycle. Here we have April rain totals in Portland from the last 10 years. We have our average line, and then we have our record driest, which was 2021, and our record wettest, which was 2022. Definitely some volatility that's going to be part of the pattern we see of climate change. We're going to have an overall increase, we think up to 10% by 2045 to 2075, but we're also going to see variation. It's going to be hard to predict the weather. We have been tracking water years for over 100 years. This is a graph showing us the difference. Here's Oregon water year, and a water year is 12 months when you track your total precipitation. So we are looking at Oregon water year precipitation anomaly relative to 1901 to 2000. So the average here of 1901 to 2000, that's our baseline, and the anomaly would be above if we get more rain. So this is precipitation anomaly percent. So this would be 10% more, 20% more. And it would be mustard colored if it's below average. So really a decrease in rain in these years. We do see a really interesting trend where it's up and down, up and down. We can also compare this to what we see in temperature during our water years to see if there's a correlation. Baseline right here. Blue line is temperature decrease from average. Red line is temperature increase from average. What's our trend? In the more recent years, we have way more hot than we do cold. We have a warming trend. We're also going to see sea level rise as our glaciers melt and our ocean ice sheets melt. We expect the sea level to rise on average 1 to 4 feet by the end of the century. That's a pretty big variation there. Oregon is expected to have up to 1 foot of sea level rise by 2050. My expectation is that you'll probably still be alive in 2050, and so that is going to be within your lifetime. We're also going to increase the number of high tide flooding events. Here I have a picture of Highway 101 in Tillamook in December 2023. I don't know if you remember how badly it flooded then, but it was a major flooding event. So now I have 2 readings for you that are thinking beyond Oregon. Both of these are focusing on island countries that are having to migrate because of climate change. And I hope you have a great rest of your day. Bye. Email me anytime with questions.